Hello everyone, welcome to Physics Pathfinder. Today we are going to cover the topic on forces and Newton's laws of motion and its application. So let's start with today's topic. We are covering forces and its application on the basis of Newton's laws of motion. So before we start today's session, let me remind you to like and subscribe my channel and press the bell icon to get the latest updates. So in our previous session on mechanics, we had covered kinematics, which only describes about how the object is in motion. That is, it describes in terms of its velocity and acceleration. But today we are going to cover the topic of dynamics, which basically talks about the effect of different forces and how does the force affect the motion of the object and its system. And we are going to see the application of Newton's law, and basically dynamics is application of Newton's laws of motion. So let's revise and go through the concepts of Newton's laws of motion in today's session and see how does it apply for forces and how does it apply the net forces in a given system. So let's see the first application, Newton's first law of motion. You would have heard about the first law of motion, which basically tells that a body in motion continues to be in motion unless it is acted upon by an external unbalanced force. So what happens if a body is not acting upon by an external unbalanced force? The net force at a given moment is zero. That means that an object can either be at rest or continue to move at a constant velocity. And in IB, we use the term called as translational equilibrium. So when an object is in translational equilibrium, your net force is zero. That is, the forces along vertical axis are balanced, are in equilibrium. That is, upward force is equal to downward force. And the forces along the horizontal, that is, the force on the right is equal to force on the left. That's how you equate, and hence the net force an object having or faced with is equal to zero. Let's see the application of Newton's second law. What does Newton's second law tells? It tells that when you're applying an external force, the net force is not zero. Then what is it equal to? It is equal to F is equal to ma. The net force F is equal to acceleration into mass, or acceleration is the net force over the mass of an object. Acceleration is change in velocity and is in the direction of the applied force or the net force. And this acceleration is inversely proportional to the mass of the object. Lastly, we are going to talk about the action-reaction. That is the Newton's third law. What does Newton's third law tell? If there are two objects A and B, then the force exerted by B on A is exactly equal to the force exerted by A on B. But since they are in opposite directions, they are equated with a negative sign. And one of them is an action, the other one is a reaction. So basically what I have seen is students, you have to consider two objects at a given time. So if a situation is a book on a table, what is the action and what is reaction? The action is the force exerted by the earth on the book. That is the weight of the object. Everybody gets this right, that weight of the object is the action. Reaction force, students generally tell the force exerted by the table on the book. Now here is a mistake. Weight is the force exerted by object A, which is earth. And object B is the book. So first you have to decide what is object A and object B. So if action is the force exerted by A on B, then reaction should be the force exerted by B on A. So your reaction should have the force exerted by book on the earth. Force exerted by earth on the book is action, then the reaction is just opposite. You have to look for keywords which should be same on both the sides. A and B should be the same. If you're swimming, the force exerted by you on the water is the action. The water pushing you forward is the reaction. So remember these things when you solve exam papers. Next, we go to the free body diagram. Now, there are certain steps to draw free body diagram. Free body diagram is basically indicating forces that is applied to an object at a given situation. So if for any object, you just consider the object as point mass, that is a dot is enough. Every object is just considered as a center of mass, that is just a dot. And from there, you indicate the direction of force by showing the array. So if you're indicating weight, you show it downwards. You indicate air resistance. If it is in equal magnitude as the weight, then the length of the arrow should be the same. The ray should be of equal length if the forces are balanced. And this can be the air resistance. So in such case, the net force is 0. The block is stationary. Now, if you're pushing the block towards the right, you will have an unbalanced force, which also can have a force of friction in the opposite direction. A little more complicated situation is the ramp. For a ramp, you have to have the situation something similar to this. So for a ramp, when an object is on a ramp, the angle made by the ramp with the horizontal, if it is theta, then the weight of the object, you can see here, weight is always exactly vertically downwards. So if the weight of the object is going vertically downwards, then the component mg cos theta goes perpendicular to the ramp and mg sine theta goes parallel to the ramp. The theta is exactly same as the theta made by the ramp. We can actually geometrically prove them as being parallel lines with transversal, and hence the theta of the ramp is equal to the theta of the component mg that you can see here. So always remember the adjacent side is cosine and the parallel side to the slope is the sine component. The direction of motion is mg sine theta, then force of friction is in the opposite direction. We are coming to force of friction in a few seconds. We are going to prove that force of friction is directly proportional to the reaction force or the force exerted by the surface on the block. And here the coefficient of friction, mu, is the constant. And R, or reaction force, is perpendicular to the block. So let's take an example, which is an exam style question. Look at this question. A wooden block of weight W rests on a rough board that produces the force of friction. At the end of the board, when it is raised up to an angle theta, the block slides down the plane of the board at a constant velocity. So here the term you have to remember, constant velocity means the net force is 0. You have to see that it is in translational equilibrium, application of Newton's first law. Which row describes the forces acting on the block as it slides down the board? Frictional force and the resultant force on the block. See that the force of friction balances mg sine theta. So your answer on one of the sections should be mg sine theta. So we have two options, A or D. The next part is the resultant force. So what do you think is the resultant force? Resultant force for a constant velocity is 0. So the answer for this should be part A. If you can see, answer is part A. Next, we are going to talk about friction. When an object is pulled, something, if you have a heavy block and you're pulling the heavy block with a force starting from 0, you pull it so much and reach till a maximum limit that now the object will start moving, and the point where it starts moving ends the first type of friction called as static friction. So static friction is the state where an object is not in motion and it is in a state of rest, and the friction is not allowing the object to move. This friction has a range of values. It has from 0 till a maximum value. And hence you can see the force of static friction is from 0 till a maximum force that you apply. Now what happens? Now the object starts sliding. The object starts sliding, the friction reduces. When friction reduces, the force of dynamic friction or sliding friction is less than the force of static friction. And what else? It is a constant. The force of dynamic friction is a constant, while force of static friction has a range of values. And we had seen that force of static friction has a range of value from 0 till mu s into r, where mu s is the coefficient of static friction, and if it's for dynamic, then it is mu d times r. You can also write this equation as mu d times r will always be proportional to mg. So you can always write this as mu times mg based on the situation. If it's on a ramp, then it's mg cosine theta. Next, coefficient of friction is, as you know, coefficient of friction is the ratio of force of friction over the reaction force. And if you remember that force of friction is balanced by mg sine theta, and the reaction force R is balanced by mg cosine theta. So instead of force of friction, you write mg sine theta, and instead of reaction force, you write mg cosine theta. Naturally, sine over cosine is tan. And you can see the angle of the ramp, if it's given to you, then coefficient of friction is also equal to tan of that angle. Okay, this is an application of Newton's third law. If you remember, I had spoken about this concept. Try to recollect and come back with an answer. So if you can see here, the force exerted by the earth on the book is force A. Then the reverse of that is the gravitational force of the book pulling on the earth. So decide the object A and object B, and just the interchanging of the forces is the action and reaction. So the answer is B. We are going to cover is called as the elevator problem. Before we go to the concept of elevator problems, let's have few rules how to solve sums based on elevator problems. So the sums goes like this. That is for two situations when the elevator is at rest or is moving at a constant velocity. The second situation is when you apply Newton's second law and the net force is not equal to 0. In such cases, the rules go like this. If I have an elevator, it is on a string, so the upward force on the elevator is the tension, and the downward force is the weight. Now, and suppose the elevator is moving down, accelerating downwards. In such situation, the rule goes like this. Identify the direction of acceleration. So it's going down in this case. the forces in the direction of acceleration is positive. So forces that is acting down is positive. That is, weight is positive. Forces opposite to the direction of acceleration is negative. That is, tension is negative. And the resultant is ma, which is the mass and the acceleration of the elevator. So how to write an equation? We'll start with the positive force, which is weight. Then go with the negative force, which is negative T. And the resultant is mass of the elevator times the acceleration of the elevator. Now think of a situation where the elevator is moving up. If the elevator is moving up, acceleration is upwards. So now the tension is positive and weight is negative. Because tension is in the direction of acceleration and weight is in the direction opposite to acceleration. So the other situation when the elevator is moving up should be exactly reverse. Positive force is tension, negative force is weight, and the resultant is ma. Now, if there is a person standing in the lift, there is a floor of the lift, the person is standing, there are, okay, let's imagine he is the person. The force exerted downward is the weight, and the force exerted by the floor is the normal force. Again, based on the direction of motion, you can see that the normal force or weight can be, any one can be positive and the other one can be negative based on the situation. Instead of tension, you can just put normal force. So if I just think of a situation where the elevator is moving up, the elevator is moving up, can you tell me which force is positive for the person? The elevator is moving up, reaction force is positive, weight is negative, and the resultant net force is equal to ma. So can you see that the normal force is nothing but ma plus w, the weight of the person. Now, what is this meaning? Normal force in this situation is called as the apparent force or the apparent weight of the person. So if you are in a lift which is at rest, your apparent force or the normal force is equal to weight. That's what you get it at home. Because at home, when you measure your weight, when you stand on a weighing machine, your normal force is equal to the weight of the object because you're not accelerating. But you take the weighing machine and go inside a lift. And if you move upwards in the lift, you measure heavier. And as against this, if the elevator is moving down, the situation goes W minus N is equal to MA. So can I tell that N is W minus NA? Apparent force is the MA, acceleration of the lift, minus the weight of the person. So can you see, when the elevator is moving upwards, you weigh heavier, your apparent weight increases, and when the elevator moves down, your apparent weight reduces. And that's what is explained in each of the situations. This is for at rest. For rest, the elevator tension is the weight of the elevator, and the normal force of the person or the apparent weight is equal to the real weight for both the situation, whether at rest or in motion. Now, if the elevator is moving upwards, he is going to weigh heavier. The person will be mg plus ma. And you can see if tension is made as a subject, that is also equal to mg plus ma. As opposed to this, if it's going down, he weighs lighter. Mg minus ma for the tension and mg minus ma for the normal or the apparent weight of the person. Quickly start applying the situation here and tell me what is the answer for tension. So if you can see here, if the elevator is moving down, weight is positive, weight is in the direction of acceleration, tension is in the direction opposite to acceleration. So what will be the equation? The equation will be W minus T is equal to ma. Make T as the subject. So it would be W plus ma, W minus ma is equal to T. So W is the weight, which is 7,500, minus 750 into 2 is 1,500. So it should be around 6,000, which is B. Next, we are going to talk about the connected masses. For connected masses, take an example here. When you have connected masses, take out each mass and try to show an FBD. So if you can see here, the condition is that M1, between M1 and M2, there is a thread. Between M2 and M3, there is another. Between M3 and from M3, you're pulling it. The net force is towards the right. Now here the assumption is the tension is T1 between M1 and M2, and there is no force of friction. So see the FBD for M1, M2, and M3. So if you can see here, for M1, T1 is the only force because we are assuming friction is negligible. So can I tell T1 is equal to the net force for the mass 1. So T1 is M1A. The object M2 is moving towards the right. So which force is going to be positive? If the object M2 is going to go towards the right, T2 is positive, T1 is negative. So can I tell T2 minus T1 is equal to M2A? And can I substitute T1 as M1A? So T2 should be M2A plus M1A. And thus, if I start solving, the answer for acceleration should be F net over M1 plus M2 plus M3. And if they have given you the masses M1, M2, M3 as 4, 3, and 1 is an example here, and the net force is 20 Newton, the acceleration is 20 over 4 plus 3 plus 1, which is 8. And the answer should be around 2.5 meter per second square. So if I get acceleration, can I find for a 3 kg mass, tension is M1A. So it is 3 times 2.5. And for M2, it is T2 minus T1 is equal to M2A. Substituting, I get the answer for T2 as 17.5 Newton. The next situation is called as an Atwood's machine. For an Atwood's machine, look at the heavier mass, decide the direction of motion, and the rules are the same. So naturally in this situation, M2 will go down. So acceleration of M2 is in the downward direction. Acceleration for M1 is in the upward direction. Try to write the equations for the situation. So on the string, whenever you see a string, tension is in the upward direction. It pulls in the opposite direction of weight. So T is always upwards. So for M1, can I write that T minus M1G is equal to M1A. In the similar way, tension is negative for the second mass because weight is positive. So M2G minus T is equal to M2A. So try to solve this FPD and go back and apply it in this situation. So here the heavier mass is Nm. So Nm side should go down and the small m side should go up. So if you keep solving, what is the equation that you get? After getting these situations, try to plug in one equation into the other, and you should come up with the solution as acceleration is equal to g into n minus 1 upon n plus 1. And naturally, tension is n minus 1 over n plus 1 times mg. You can look for a detailed solution. So the answer is C. With this, we come to an end of today's session. Do watch part 2 for more exam style questions and examples related to forces and Newton's laws of motion. See you then. Bye-bye.